Next, I will explain the function of the interferometer, which is the most important part of the Fourier transform infrared spectrophotometer, or FTIR. The infrared light emitted from the light source is split into two by the beam splitter. The infrared light is reflected by the fixed mirror and the moving mirror, mixed again by the beam splitter, passes through the sample, and is detected by the detector. If there is an optical path difference between the light reflected by the fixed mirror and the light reflected by the moving mirror, the mixed light causes interference. FTIR detects changes in infrared light intensity due to interference as a function of optical path difference. First, let's use monochromatic light to explain how the light that enters the interferometer interferes. If there is no optical path difference between the fixed mirror and the moving mirror, the light reflected by the two mirrors will be in phase. Therefore, the maxima and maxima coincide, so combining these two waves strengthens each other. Next, we will explain the interference when the optical path difference between the moving mirror and the fixed mirror is half a wavelength. The position of the light reflected by the fixed mirror does not change. However, the light reflected by the moving mirror is displaced by exactly half a wavelength. Then, the maximum of one wave is in agreement with the minimum of the other, and the amplitude of the composite wave is zero. This is when the optical path difference between the moving mirror and the fixed mirror is exactly one wavelength. At this time, the maximum and the maximum of the two waves, or the minimum and the minimum of the two waves are the same, so when these two waves are combined, they strengthen each other. In this way, the intensity of the light reflected by the two mirrors becomes a single sine curve that maximizes each time the optical path difference becomes an integral multiple of the wavelength. As shown in the previous slide, when monochromatic light is introduced into the interferometer, a time-varying output that oscillates with a single sine curve as shown in A is obtained. Next, when dichroic light is introduced into the interferometer, it becomes a composite wave of the trigonometric function shown by the red line and the trigonometric function shown by the blue line, and waviness occurs as shown in B. Third, as shown in C, I will explain the case where continuous light with a continuous light intensity is introduced into the interferometer. The intensity of the output light becomes maximum at the time when the optical path difference becomes zero. This point is called center burst. After that, as the optical path difference increases, the intensity decreases while oscillating up and down, and finally converges to a constant value. This waveform is called an interferogram. Conversely, a mathematical process called the Fourier transform is used to obtain a spectrum representing the relationship between wave number and light intensity from the measured interference signal. Fourier transform of a single sine curve gives a spectrum with intensity at only a specific wave number. Fourier transform of the composite wave of the two sine curves gives a spectrum with intensity at two wave numbers. Generally, the Fourier transform of an interferogram yields a spectrum that represents the intensity distribution of light as a function of wave number or wavelength. In this way, FTIR obtains a spectrum that represents the intensity of infrared light by Fourier transforming the time change of the intensity of the interference wave output from the interferometer. Next, let's confirm the relationship between the waveform and the spectrum obtained by Fourier transforming it by experiments using sound waves. For this experiment, we used software called Frequency Generator on the right side of the screen and software called Audio Analyzer on the left side of the screen. A frequency generator is a software that allows a speaker to produce a sound with a specific frequency. The audio analyzer shows the waveform of the sound input from the microphone at the top of the screen and the frequency obtained by Fourier transforming the waveform at the bottom of the screen. First, let's make a sound of 200 Hz. In the upper left of the screen, the waveform is displayed with a red line, which is a little difficult to see. The spectrum is shown in the lower left. The horizontal axis is a logarithmic scale, and the memory to the right of 100 Hz represents 200 Hz. Now I'm increasing the frequency to 500 Hz. In the lower left figure, you can see that there is a peak at 500 Hz. The waveform becomes easier to see when the frequency is increased. Now it's 1000 Hz. There is a sharp peak at 1000 Hz. The frequency is increasing and it is now 2000 Hz. You can see that the spectrum is a little overtone. Further increase the frequency. Now it's 4000 Hz. It is represented by a single sine curve as shown above. As the sound gets higher and higher, it becomes harder to hear. If it exceeds 10,000 Hz, your ears will hurt. The human audible range is said to be 20 to 20,000 Hz. However, as it ages, it becomes harder to hear high sounds. I seem to have a limit of about 13,000 Hz. Next, let's look at the waveform and spectrum when synthesizing sound waves of two frequencies. I am stacking 1000 Hz and 2500 Hz. As shown in the upper left, you can see the undulating waveform, and in the spectrum, you can see peaks at 1000 and 2500 Hz, as shown in the lower left. Next, let's take a look at the spectrum called the white noise, which is represented by the superposition of sounds of many frequencies. Thus, a continuously distributed spectrum is observed. Let's return to FTIR and summarize the Fourier transform. The Fourier transform is a mathematical operation that decomposes a function into a superposition of sinusoids. This process is used to obtain spectra from the interferogram in FTIR. In the actual FTIR, two functions are important when measuring the infrared absorption spectrum. One is called an interferogram, which is a function measured directly by the device. It represents the intensity I of the light emitted from the Michelson interferometer as a function of the optical path difference x. And the other is spectrum. This is the intensity B of the light emitted from the light source expressed as a function of the wave number, nu bar. There is a Fourier transform pair relationship between the interferogram I, x, and the spectrum B, nu bar. Expressed as an equation, it becomes as shown in equation 1, and the Fourier transform of the spectrum gives an interferogram. Conversely, if the interferogram is Fourier transformed, the spectrum is obtained as shown in equation 2. In this way, in the spectrum measurement by FTIR, first the interferogram is directly measured, and the Fourier transform is performed to obtain the spectrum. Since many FTIRs use the single beam method, it is necessary to measure the incident light intensity, I0, and the transmitted light intensity, I, after being absorbed by the sample separately. First, measure the background interferogram without sample. Fourier transform it to get the background single beam spectrum. The intensity of the light from the light source is continuously distributed in this way, but in some places, the intensity drops sharply due to absorption by infrared active gas molecules such as water vapor and carbon dioxide existing in the air. Then insert the sample and measure the interferogram of the sample. Fourier transform it to get the single beam spectrum of the sample. If you take the ratio of these two, you can get the spectrum of transmittance, I over I0. In addition, the transmittance can be converted into an absorbance spectrum using this formula. Next, let's take a look inside the actual FTIR. This is FTIR called Excalibur, manufactured by Biorad. About 20 years after purchase, the front line has already retired, but it can still be used for measurement. This part is the measurement room. There is a light source and an interferometer in this part. Light from the interferometer enters from the right, passes through the sample, and is detected by the detector located on the left. Take a closer look inside. This is an interferometer. Here is the light source. The light source cannot be seen from this position, but the light emitted from the light source is reflected by this mirror and passes through this hole. You can see the light from the light source when you insert the camera. Then it is reflected by this mirror and enters the interferometer. Here is the beam splitter. A beam splitter splits the light from the light source into two. This part is the electromagnet for moving the moving mirror. You can see that the moving mirror is attached to the tip part and it moves finely. The position of the moving mirror is determined by adjusting the current flowing through the coil. The fixed mirror is behind this, but you can't see it. This is a helium neon laser. The light of the helium neon laser also enters the interferometer and is used to measure the track difference. Infrared light from the interferometer passes through here and is reflected by this mirror into the sample chamber. Place the sample on this side. Then, it is reflected by this mirror and detected by the detector seen in this part. This slide shows the path of infrared light and the helium neon laser. The light emitted from the infrared light source is reflected by this mirror and enters the interference system. The beam splitter mixes the reflected light from the moving mirror and the reflected light from the fixed mirror, and goes to the sample side. And here is a mirror with a hole in the center. Since the infrared light is divergent, it is reflected by the mirror around the hole to the sample chamber, and finally detected by the infrared light detector. On the other hand, the light of the helium neon laser is reflected by a small mirror here and enters the interferometer. The path after this is the same as infrared light. However, the light of the helium neon laser does not spread, and the interference wave is observed by the detector for the helium neon laser through the hole in the center of this mirror. The light of this helium neon laser is used to determine the timing of sampling the interferogram whose intensity is measured at regular intervals. The wavelength of the helium neon laser is 632.8198 nanometer, which is extremely stable and enables highly accurate position and length measurement. The fringe pattern of the helium neon laser is as shown in the middle figure, and since it is monochromatic light, it shows the intensity change represented by a single sine wave. Then, sampling is performed at an intensity midway between the maximum intensity and the minimum intensity. Then, the interferogram will be sampled every half wavelength of the helium neon laser. Sampling is performed every 316.4 nanometer, which is a half wavelength of this wavelength. The position can be determined with an accuracy of micrometer or less. When the intensity comes between the maximum and minimum, the interferogram is sampled at regular time intervals. Therefore, the time indicated by the black dot is the time to actually make the measurement. The interferogram thus measured is Fourier transformed to obtain a spectrum. The wavelength of the helium neon laser is determined with high accuracy, and the oscillation wavelength is very stable. Since the wave number is calculated based on the wavelength with high accuracy as described above, the wave number accuracy of the spectrum measured by FTIR is extremely high. Next, we will summarize the advantages of FTIR when compared to a distributed infrared spectrophotometer. First, since the total wave number is detected at the same time, the intensity of the detected light is high, and a spectrum with a high SN ratio can be obtained. That is, a clean spectrum with little noise can be obtained. This is called multiplex advantage or Felget's advantage. Also, since all wave numbers are measured simultaneously, there is no time lag between wave numbers, which is advantageous for tracking reactions. Secondly, since the slit is not used, the amount of light that reaches the detector is large, so the SN ratio is high. This is called throughput advantage or Jacquinot advantage. Third, the wave number accuracy of the spectrum is high. This is because the optical path difference is calibrated using the interference of the helium-neon laser. Fourth, the wave number resolution can be increased. The resolution of FTIR is determined by the moving distance of the moving mirror, and the resolution that is inversely proportional to the moving distance can be obtained. For example, moving the moving mirror by 1 cm gives a resolution of 1 Kaiser, and moving it by 1/2 cm gives a resolution of 2 Kaiser. In this way, the resolution of FTIR is determined by the moving distance of the moving mirror. Therefore, unlike the distributed type, which requires a narrow slit, the resolution can be increased without sacrificing the SN ratio. Finally, I will summarize the contents of today's class. Today, I explain the mechanism of the infrared spectrophotometer. Infrared spectrophotometers are available in dispersive and Fourier transform types. However, because the Fourier transform type has more advantages, the Fourier transform type is now the mainstream, and the dispersive infrared spectrophotometer is rarely used. In Fourier transform infrared spectroscopy, or FTIR, the interferogram, which is the intensity of the interfering infrared light, is first measured and then Fourier transformed to obtain the spectrum. Finally, we will give you exercise questions. Illustrate the time change of the output light intensity when 2000 Kaiser infrared light is incident on a Michelson interferometer with a moving mirror that moves at 0.1 cm/second. However, there is no optical path difference at t equals 0. Use relative intensity on the vertical axis. Please solve this problem and submit your report through the web class. So, this is the end of today's class.